So we continue with our discussion on quasi-phase matching. So before I start, do you have any questions from the earlier lectures? Okay, so let's continue with our discussion on quasi-phase matching. Also called QPM. So let's recall the electric field at the second harmonic satisfies an equation given by I omega d by c n 2 exponential minus I delta k times z, where delta k is equal to k2 minus 2k1, which is equal to 2 omega by c n at 2 omega minus twice omega by c n at omega, which we had also written as 2 omega by c n2 minus n1. So delta k is a phase mismatch between the waves at omega and 2 omega, and depends on the refractive indices of the medium at frequency omega and at frequency 2 omega. N1 is n of omega, the refractive index of the medium at frequency omega, and N2 is n of 2 omega, the refractive index of the medium at frequency 2 omega. What we also saw is that because of this term, so there is an E1 square here. Because of this term, the amplitude of the second harmonic field does not grow continuously but oscillates. So let's recall we had a curve looking like this. This is Z, and I can write here either the power in the second harmonic or the efficiency. It goes up and down periodically. This distance was called LC. This is 2LC. LC is the coherence length of this interaction process, and is given by LC is equal to pi by delta k. So what is actually happening is, as we discussed last time, the second harmonic electric field grows until a certain distance LC, at which point the phase difference between the nonlinear polarization at frequency 2 omega and the electric field at 2 omega becomes pi, and beyond this point the nonlinear polarization actually feeds energy into the second harmonic, which is out of phase with the existing electric field, resulting in a drop in the electric field of the second harmonic. The electric field of the second harmonic becomes 0 at 2LC and then again starts to grow. We also saw that if you take typical values of refractive indices at frequency omega and 2 omega, because of dispersion, the peak efficiency that you can get is extremely small. So it is extremely important to make sure that delta k is 0 or very close to 0, so that the efficiencies can be reasonably high. Now, if you can make delta k is equal to 0, we get what is called the Birefringence phase-matching, which we have seen earlier, but I can actually use another technique to achieve what is called as quasi-phase-matching. So in this equation, what we would like to do is to make d a function of z and a periodic function of z. So last time we saw that if I take a d of z is equal to d0 sine kz, where k is the spatial frequency of this variation and given by 2 pi by lambda, where capital lambda is the period of the variation of d, then what happens actually is that at this point, instead of the second harmonic decreasing in amplitude, it grows again, continues to grow up to this point, and then again instead of dropping down, it continues to grow. So there is an increase of the efficiency of the second harmonic generation, because every time you have a phase difference of pi between the nonlinear polarization and the electric field, you introduce a change of sign of d, which is essentially a change of phase of pi of the nonlinear polarization term. So this way you can actually overcome this decrease in efficiency, and this technique is called quasi-phase matching. So remember what we had done was we substituted this expression for D in this equation, and if you write the sign in terms of two exponentials, what you find is you have one exponential term which is exponential I capital K minus delta kz, and you have another exponential term exponential I minus I k plus delta kz. So if I can make capital K is equal to delta k, one of these terms has no phase term, and that term, when I integrate this equation, gives me an increasing electric field of the second harmonic. So what is the spatial frequency required for phase matching or quasi-phase matching? K is equal to delta k. This implies that 2 pi by lambda is equal to delta k, which is 2 omega by c into n of 2 omega minus n of omega, or lambda is equal to pi c by omega into n of 2 omega minus n of omega, which is equal to pi c by omega into n2 minus n1. This period of quasi-phase matching depends on the refractive indices at the frequency omega and 2 omega, and also of course the frequency omega itself. We had seen last time that if you take a typical wavelength of 800 nanometers, we can calculate what is the capital lambda required in the case of lithium niobate, and we found it's of the order of 3.3 microns or so. So this is a very small period required, which means you need to change the direction of the sign of the D coefficient every 3.3 microns or so. Also note that this particular period depends on the frequency or the wavelength. So if you take second harmonic generation of 800 nanometer wavelength to generate 400 nanometers, I need to know the refractive index of the medium at 800 nanometers, N1. I need to know the refractive index of the medium at 400 nanometers, which is N2, and then I can substitute into this equation and get the period. Now, if you change this wavelength slightly, say from 800 to I change it to 810 nanometers, then note that the frequency will change, the refractive indices will change, and so the required capital lambda will also change. So what this implies is that if you take a particular fundamental wavelength, calculate the corresponding grating period required for quasi-phase matching, and make a device with that particular period, that device will work perfectly at the chosen frequency at which you have designed the substrate. So at 800 nanometers, if you calculate the period and make a periodic reversal of sign of D at the period corresponding to 800 nanometers, it will work perfectly at 800 nanometers. Now, if you change this input wavelength, the period that you have in your crystal does not correspond to the period required for the new wavelength. In this case, what will happen is the efficiency will drop down, because that capital K corresponding to what you have made in the crystal does not correspond to what is required to quasi-phase match the new frequency. So this is the frequency dependent period here. So for any particular input frequency, if you want to generate second harmonic, you need to calculate the corresponding quasi-phase matching period and make a device with that period. And of course, as you will notice that this will have a certain bandwidth, which means that if your frequency deviates from the chosen frequency at the input, then the efficiency will drop down. I'll come back to this point a little later. Now, what happens is, to create a sinusoidally varying D coefficient is not very easy, because remember, materials have a certain nonlinear coefficient, and how do I make it sinusoidally varying along the propagation direction? So what is done now is, instead of having a sinusoidal variation in D, I choose a periodic variation in D. Periodic variation in D. and actually I can have crystals with d positive or negative. Remember, d is one of the elements of the nonlinear tensor. The sign of the d coefficient depends on the orientation of the axes. So you can actually change the sign of d by changing the orientation of the crystal axis. So it is possible to have d variation which is either plus or minus, and so let me consider a situation where I have, if I plot d versus z, let me assume I have a variation like this. So this is plus d and this is minus d, this is the period and this is length L. So in one period I have positive value of d over a length L, and over a length lambda minus L I have a negative value of d. So d of z is plus d0 for mod z less than L by 2 and is equal to minus d0 for L by 2 less than mod z less than lambda by 2. So that is a periodic function, function with a period capital lambda, and this ratio L by lambda is called the duty cycle. So over a length L the nonlinear coefficient is positive, and over a length lambda minus L the nonlinear coefficient is negative, and the function is periodic. So d of z plus lambda is equal to d of z. Now because this is a periodic function, I can always make a Fourier series expansion. So if I want to write a Fourier series expansion, I can write d of z as d0 sigma gm exponential I m k z. This is the periodic function with a fundamental period capital lambda, and so fundamental spatial frequency 2 pi by capital lambda. So when I make a Fourier series expansion of this d as a function of z, I will leave it as a problem to you that you can actually show that this is d0 sigma gm exponential I m k z with m going from minus infinity to plus infinity. This is an exponential Fourier series. Instead of writing sine and cosine Fourier series, I am using an exponential Fourier series, and what I would like you to do is take this periodic function and calculate the Fourier coefficient gm, and I would like you to show that gm is equal to 2 by m pi sine m pi L by lambda. These are the Fourier coefficients corresponding to various values of m. So actually d of z can be written as d0 times g0 plus g1 exponential I k z plus g minus 1 exponential minus I k z plus g2 exponential 2 I k z plus g minus 2 exponential minus 2 I k z plus g3 and so on. These are the various Fourier terms in the expansion, and the various coefficients, Fourier coefficients, are given by the value of gm which is written here. So, and of course this depends on the duty cycle small l by capital lambda. So if you take for example a duty cycle of half, that means over a length capital lambda by 2 I have a positive value of d, and over a length lambda by 2 again I have a negative value of d. So duty cycle of 50%, which means half the period the nonlinear coefficient is positive, the other half it is negative with the same magnitude. Then what you can see here is from here g1 is equal to 2 by pi, g minus 1 is minus 2 by pi. What is the value of g2? Note, if L by lambda is half, g2 will have a sign pi term, that will be 0, so g2 is 0. G minus 2 is 0, In fact, you can show that all even series, even terms in the expansion are 0, giving you only the odd terms in the expansion. Similarly, G3 will be 2 by 3 pi sine sine 3 pi, but 3 pi by 2, which is minus 2 by 3 pi, and so on. So you can find out all the expansion coefficients in Fourier series. So please do derive this equation here, find out what are the Fourier terms in the expansion. So instead of having a purely sinusoidal variation in the nonlinear coefficient, we have a periodic variation, and that periodic variation can be written as a Fourier series, and this series contains many exponential terms here. So let me see what happens with this expansion. So let me write again the equation for E2. dE2 by dz is I omega d by Cn2 E1 square. Okay, now d I need to substitute here. So d is a function of z exponential minus I delta kz, which I write as I omega by Cn2 d0 E1 square sigma gm exponential I mk minus delta k z. So if I want to write the first few terms, so I have omega d0 by Cn2 E1 square into G0 plus G1 e to the power I k minus delta k z plus G minus 1 exponential minus I k plus delta k z plus G2 e to the power I 2k minus delta k z plus so on G minus 2 e to the power minus I 2k plus delta k z and so on. Now I can integrate this equation. Sorry, there is a exponential minus I delta k z here. For G0, there is no exponential I k z here. I still have an exponential minus I delta k z. So I can actually integrate this equation, assuming again, like we did before, that the change in the energy of the fundamental frequency omega is negligibly small, which means the efficiency is small, and in that case I can assume E1 square to be a constant, and I can immediately integrate this equation to get the following expression. So E2 of z is equal to I omega d0 by Cn2 E1 square. So let me now skip a few steps. I can actually integrate and from 0 to z, and what you will get is G0 exponential minus I delta k z by 2 into sine delta k z by 2 by delta k by 2. I have integrated and simplified exactly like we did before, plus I will have G1 exponential I k minus delta k z by 2 sine k minus delta k z by 2 by k minus delta k by 2 plus G minus 1 minus I k plus delta k z by 2 into sine k plus delta k z by 2 by k plus delta k by 2 and so on. Okay. So I can actually integrate this equation, because if I assume E1 square is a constant, then the only term that I need to integrate are these terms here, and I get this sine delta k z by 2 by delta k by 2 and so on. Now what I can do is, in quasi-phase matching, what I try to do is I choose a value of capital K such that one of these sine terms, terms becomes just disappears from here, which means, for example, if I choose capital K is equal to delta k, then this term will give me, what will be the value of this term when capital K is equal to delta k? This will be z. This factor, remember here it is sine delta k minus delta k z by 2 by k minus delta k by 2, So, if I multiply and divide by z, this becomes a sinc function, and at the 0 argument the sinc function is 1 and I get z. But all the other terms will still have a finite sign term here sitting here, and so I can neglect the contribution of all the other terms, and what I will be left with is E2 of z will be approximately given by, if I can neglect all the other terms, and if I choose capital K is equal to delta k, I will have I omega by Cn2 d naught g1 E1 square into exponential I. So, k is equal to delta k. So, this goes off and I have simply z plus the other terms which are neglected. So, note here that the expression that I get is very similar to the situation when delta k was 0, except that now the nonlinear coefficient, instead of being d0, is now d0 times g1, where g1 is the Fourier amplitude of the exponential I delta k I kz term, the first Fourier expansion coefficient, and it is proportional to length here. So, as the length increases, as I showed you before, the second harmonic field will keep on increasing. This is exactly what it is being shown here. This is keep on increasing because of quasi phase matching. Remember, if there was perfect phase matching, this should have gone like this. It should have been continuously increasing, but it's increasing much slowly because the effective nonlinear coefficient now becomes d0 times g1. So, if you choose the first this capital K is equal to delta k, g1 is equal to 2 by pi. So, the effective nonlinear coefficient becomes 2 by pi d0. Okay, and if I can neglect other terms, what you can see here is that the second harmonic field now grows with z, and I will have much higher efficiencies than if I did not have phase matching or if I did not have quasi phase matching. So, by choosing capital K is equal to delta k, what I am essentially doing is making one of these sign terms give me z here instead of an oscillatory solution, and my second harmonic field grows rather than being oscillatory. Because I am choosing the first Fourier coefficient capital K is equal to delta k, this is called first order quasi phase matching. So, if I choose k is equal to 2k, so sorry, k is equal to delta k, this is first order QPM. If I choose 2k is equal to delta k, this is called second order QPM. And if I choose 3k is equal to delta k, it's called third order QPM. So, what I have calculated is for a first order QPM, if you took a second order QPM, I will have d0 times g2 here. If I choose a third order QPM, I will have d0 times g3 here. Now, please note that as you go to higher Fourier coefficients, the amplitude of the Fourier term keeps on dropping down, because I have just calculated gm is 2 by m pi sine m pi l by lambda, and if you have larger values of m, you have an increasing denominator here. So, g1 is 2 by pi, g3 is 2 by 3 pi, g5 is 2 by 5 pi, and so on. But what is the advantage of going to higher order QPM? So, for example, if I were to use first order QPM, I need to choose k is equal to delta k, which is equal to k is equal to 2 pi by lambda. So, the period required is 2 pi by delta k. And what is pi by delta k? Pi by delta k is the coherence length. So, this is twice LC. That is visible from here, that I need to have the period to be twice LC. I need to change the sign of the d coefficient after half the coherence length here, and then I get quasi phase matching. And so, if the coherence length is 3.3 microns, I need to have a periodicity of 6.6 microns. Every 3.3 microns, I need to reverse the direction or change the sign of d. If I were to use third order QPM, then I need 3k is equal to delta k, which is equal to 6 pi by lambda. So, lambda is equal to 6 pi by delta k, which is equal to 6 times LC. I gain in terms of the period required for quasi-phase matching. Remember, to fabricate this is not so easy. So, I need to worry about fabrication problems. So, if I need to reverse the sign of d coefficient every 3.3 microns, it is much more difficult than to do at 6 times LC, which is about 19 microns or so. So, it is much easier to make third order quasi phase matching than first order quasi phase matching, but what is it? What is the price I pay? You see here that the nonlinear coefficient, effective nonlinear coefficient, instead of being 2 by pi d0 for first order QPM, becomes 2 by 3 pi d0 for third order QPM. And because the efficiency of second harmonic generation depends on the square of the nonlinear coefficient, note that the second harmonic power is proportional to E2 square, and E2 square is proportional to D0 G1 whole square. It's proportional to G1 square or G3 square, GM square. So, if I go to higher order quasi phase matching, the corresponding Fourier coefficients have smaller magnitudes and the effective nonlinear coefficient will be smaller. And so, the efficiency will decrease as you go to higher order QPM. So, already if you are perfectly phase matched, the effective nonlinear coefficient will be D0. If you have first order QPM, the effective nonlinear coefficient is 2 by pi D0, and because the efficiency goes up as G1 square, it will be 4 by pi square times the efficiency if you had perfect phase matching. And pi square is of the order of 10, so 4 by pi square is about 0.4, that's 40%. So, if you have perfect phase matching, you have a certain efficiency. If you go to first order QPM, your efficiency drops down by 40%. If you go to third order QPM, it becomes another 1 by 9 times smaller, and that means another 10 times factor of 9 times decrease in efficiency. And so, of course, it's easier to make third order QPM structures, but the price you pay is in terms of efficiency. Now, I didn't talk about G2 because you note here that if you choose a duty cycle of half, if L by lambda is half, then all even order coefficients are 0. So, there is no G2. So, there is no G2. So, in this expansion here, if your duty cycle is half, G2 is 0. So, there is no you may be achieving second order quasi phase matching, but the effective nonlinear coefficient is 0. So, you will not generate second harmonic if you choose a duty cycle of half. So, I want to leave another problem to you. Please find out what is the best duty cycle that I must use, so that I am able to use the second order quasi phase matching term. So, what should be the value of if I go back and look at this expansion here, what should be the value of L by lambda? What should be the value of L by lambda here, so that I can have a finite value of G2 and the maximum G2 that is possible. So, I leave this problem to you and then correspondingly calculate what is the drop in efficiency if I do second order QPM in comparison to the phase matched interaction process. Okay. Now, so for example, if I were to take the first order QPM, then I can calculate. I had this expression here. Let me write it again. Yeah. So, this is the expression for E2 of Z. So, from here I can actually calculate the second harmonic power. So, P2 of Z is equal to N2 by 2 C mu 0 mod E2 of Z whole square into the area. So, this is equal to N2 by 2 C mu 0 omega square by C square N2 square D0 square G1 square E1 mod 4 Z square. Okay, if I don't take exactly delta k is equal to capital K is equal to delta k, I will have essentially a term like instead of z square, I have sine k minus delta k z by 2 by k minus delta k by 2 whole square. If k is equal to, if capital K is equal to delta k exactly, then this becomes z square. Otherwise, there is a sine term which comes here. I can replace E1 square in terms of P1. Remember, the fundamental power is N1 by 2 C mu 0 mod E1 square into area. So I can substitute into this equation and calculate the corresponding efficiency of second harmonic generation P2 of Z by P1. P1 is assumed to be independent of Z because I am neglecting the amount of power that goes from the fundamental to second harmonic. I am neglecting the changes in E1 as a function of Z. Please remember that I cannot generate second harmonic unless I lose power from the fundamental. So E1, if E2 changes, E1 has to change, but I am neglecting the change in E1 to be able to integrate that equation so that I get an expression for efficiency. So you can again substitute in terms of P1 and calculate. So the only difference from perfect phase matching you will see is instead of sine delta k z by 2 by delta k by 2 whole square, I am getting sine k minus delta k z by 2 by k minus delta k z by 2. So delta k gets replaced by k minus delta k, and the nonlinear coefficient gets replaced by d0 times g1 for first order QPM. So I can use this process, quasi-phase matching, to cancel the effects of delta k by an appropriate period of reversal of the sign of d coefficient. In birefringence phase matching, I needed to have a medium which has a birefringence. There must be an ordinary wave, there must be an extraordinary wave. And the fundamental and second harmonic are to have orthogonal polarization states. But here, please note that I am not using any birefringence. If there is a finite value of delta k between the fundamental and second harmonic, for example, if they have the same polarization, then if the medium is anisotropic and if they have the same polarization, lithium niobate, let me assume the omega frequency is extraordinary wave. The 2 omega frequency is an extraordinary wave. Obviously, I cannot have birefringence phase matching because the extraordinary refractive index at omega and the extraordinary refractive index at 2 omega are not equal. So delta k is not equal to 0. But if I can change the sign of capital small d periodically with a period capital lambda having a spatial frequency capital K, then which is equal to delta k, then I will have this becoming z squared and have a very good efficiency. So that's the advantage of quasi-phase matching, that I don't depend on the birefringence of the crystal, and I can actually have a crystal which is isotropic, or in an anisotropic medium I can have interaction from omega to 2 omega for waves having the same polarization states and so on. So that's the advantage of QPM, and this is now a very, very standard technique for most third order nonlinear processes. Now I want to mention to you one thing, that suppose I were to choose first order QPM. So k is equal to 2 pi by lambda is equal to delta k. So this is equal to 2 omega by c, n of 2 omega minus n of omega. So the period required is pi c by omega into n of 2 omega minus n of omega. So as I mentioned to you before, the spatial period required for quasi-phase matching depends on the fundamental frequency. So if I take a crystal and if I launch certain omega, the sign reversal of d positive negative depends on the frequency. If I vary the input frequency slightly, the required period is different from the period that exists in the medium, and the efficiency will drop down. So in fact, if you were to plot the efficiency as a function of frequency, what you will get is a curve like this. This is the frequency omega 0 for which you have chosen the capital lambda, and at a certain frequency separated from here by delta omega, assuming delta omega much less than omega 0, the efficiency will drop to 0. In fact, you can look at this equation and tell me what is the value of delta k at which the efficiency will drop to 0. The efficiency will drop to 0 when the sign function becomes 0, that is k minus delta k into, if a crystal length is L, k minus delta k into L by 2 is equal to pi. So, I can immediately calculate. So, when k minus delta k into L by 2 is equal to pi, the efficiency becomes 0, and that means delta k is equal to k minus, actually plus minus pi. So, delta k is equal to k plus or minus 2 pi by L. And this k, delta k is a function of omega. Please note that delta k is a function of omega. So, in this curve what I have drawn here is, this is the frequency at which I have designed my quasi phase matching period, for which capital K is equal to delta k. As I move away from here, delta k changes, and when delta k becomes k or plus minus 2 pi by L, the corresponding efficiency becomes 0. So, I can bandwidth of this interaction process, which is approximately delta omega, over which the second harmonic, this quasi phase matching crystal will work efficiently. So, if you were to deviate your input frequency by more than of the order of delta omega, then the efficiencies of second harmonic generation will become very poor. The longer the crystal, the narrower is the bandwidth of second harmonic interaction process. So, if you take a long crystal with a domain reversed crystal, then the bandwidth is much narrower than if you have a shorter crystal. So, again what I would like you to do is, please note that, let me give you a problem. The problem is, at omega is equal to omega 0, delta k of omega 0 is equal to k. This is equal to 2 pi by lambda. At omega is equal to omega 0 plus delta omega, delta k of omega is equal to k plus minus 2 pi by L. Okay, plus or minus, you find out. So, if delta omega is much less than omega 0, from this expression here, you can write delta k of omega is equal to delta k of omega 0 plus delta omega, make a Taylor series expansion, use this equation here and calculate delta omega, an expression for delta omega. What is the bandwidth of the interaction process in terms of the refractive indices or in terms of whatever it is. So, I will leave it as a problem to you to calculate what is the bandwidth of this interaction process, how does, in terms of frequency, delta omega or delta lambda. Okay. So, this is important in a practical device, because I need to know how precisely I need to control the frequency of the input laser, so that I keep having high efficiency second harmonic generation. Okay. Now, obviously the question arises, how do I change the sign of D? Now, there is a standard procedure now which is employed. So, let me take an example of lithium niobate, LiNbO3. This crystal is a ferroelectric crystal. So, it has a spontaneous polarization, and for example, let me call this as z axis of the crystal. So, x may be here and y may be here. So, these are the three principal axes of the crystal x, y, z. It is a uniaxial crystal. So, the optic axis is along z axis, and what happens in this crystal is there is a spontaneous polarization that is there along the z axis. Now, what I can do is, if we apply a very strong electric field in the reverse direction, suppose I apply a strong electric field in the downward direction, I can actually reverse the direction of the z axis by flipping the atoms within the crystal. And what happens is, for example, if I take this half of the crystal and if I apply a very strong electric field in the downward direction, then I can change the orientation of the z axis from pointing up to pointing down. It is just like in magnets, you have north pole, south pole, and if you can flip it out and to make it south pole, north pole by applying a very strong magnetic field in the reverse direction. So, you can actually change the orientation of the spontaneous polarization direction by applying a very strong electric field in the opposite direction. So, one of the techniques is called electric field polling. So, what you do is you apply, you put in periodic electrodes. So, this is a crystal with having say z axis like this originally. So, you apply you connect all this and apply electric field in the downward direction. When you apply a strong enough electric field, what happens is the optic axis in these positions reverses its direction. So, here there is a strong electric field in the downward direction which changes the z axis from pointing up to pointing down, and similarly here again there is a strong electric field from pointing up to pointing down, and this is the period of domain reversal. So, this is called periodic polling. That means you are polling the crystal orientation periodically, and so these are called periodically poled crystals. And in fact, this is called periodically poled lithium niobate. If it is the lithium niobate, also called in short form as piplins, that means these are lithium niobate crystal in which the direction of the spontaneous polarization is periodically reversing in the crystal. But please note that the linear property of the medium is the same along the z direction, along this direction, but its optic axis is reversing its orientation. So, what is the effect of this direction change of optic axis? Again, please note that the D tensor we have written, Dijk, it is a tensor and it is written in the principal axis system. So, in the principal axis system, the coefficients, D coefficients are all written in the principal axis system. So, if I were to consider a crystal with two parts, for example, in one part let me assume the z axis was here, this is x and this is y, and in the other part I had z like this, y like this and x like this. I have changed the direction of z, I have to keep the right handed coordinate system. So, in this coordinate system here, the D tensor which I have written is valid. In this coordinate system, the D tensor which I have written is also valid, provided I choose this coordinate axis. But please note that my equations which I am writing are in a laboratory coordinate system. So, they could be like this. For example, this could be x, y, z. Let me call this as capital Z, capital X, capital Y. This is the principal axis system, this is the laboratory coordinate system. So, in this part of the crystal, the laboratory coordinate system and the crystal principal axis exactly match. So, the D tensor written in the principal axis system is also the D tensor in the laboratory coordinate system. In the second part of the crystal, the laboratory coordinate system and the principal axis system do not coincide. The D tensor is written in the principal axis system. So, I need to transform the D tensor from the principal axis system to the laboratory coordinate system. So, what do? I use the transformation properties of tensors. Note that between these two, all I have done is to change x to minus x, z to minus z, and keep y the same. So, this system and this system are related through x to minus x and z to minus z and y to plus y. So, I leave it as a problem to you that please calculate when you rotate the principal axis system around the y axis by 180 degrees, which are the elements of the D tensor which change sign, which are the elements of the D tensor which do not change sign. That means, I need to write the D tensor of this part of the crystal in the laboratory coordinate system and compare that with the D tensor of this half, and you may find that some of the tensor elements do not change sign, some of them would have changed sign. So, those elements which have changed sign, I can use them for quasi-phase matching. If the particular nonlinear coefficient does not change sign, obviously I can't use that for quasi-phase matching. So, please go back and look at your earlier notes on tensor analysis, find out how to transform tensors. It is very simple, it is not a general angle, it is just x to minus x, z to minus z, y to plus y, and so you can actually use this transformation properties of tensors to find out which Dijk elements here are negative of here and which Dijk elements do not change sign. And you will see, for example, T33 is the largest nonlinear coefficient lithium niobate, and that changes sign. So, you can actually use D33 for quasi-phase matching. Okay, so please go back and do, in case you have a problem, we can discuss that in the class and analyze this a little more carefully. Okay, do you have any questions in quasi-phase matching? So, let me just recollect. What we have done is, in the equation for second harmonic, there is an exponential minus I delta kz. When I integrate over length, this exponential factor gives me an oscillatory solution, and to remove this oscillatory solution, I must make delta k is equal to 0. If I choose delta k is equal to 0, the second harmonic power grows quadratically with length, and I have very high efficiencies. And the way to achieve this is called Birefringence phase matching. Now, the problem with Birefringence phase matching is I need the crystal has to be anisotropic, and the polarization states of the omega and 2 omega are orthogonal to each other, which means there are some D elements, some D tensor elements which are responsible for this interaction, and they may not be the largest. So, to overcome this problem, we have discussed quasi-phase matching, in which I do not take a crystal with a uniform D value, but I periodically reverse the sign of D, the nonlinear coefficient. By doing that, I can use this periodic variation in D to cancel the effects of exponential minus I delta kz, and I can achieve quasi-phase matching, and then I do not have to have a birefringent crystal. I can use the same polarization state for omega and 2 omega and achieve a very good conversion efficiency. So, the period required for this quasi-phase matching depends on the frequency of which you want to do second harmonic generation, and it also depends on the refractive indices of the medium at omega and 2 omega. You can do first order quasi-phase matching, you can do third order quasi-phase matching, and so on, and of course, you pay a price compared to perfect phase matching, and the price is in terms of efficiencies, because there is an effective nonlinear coefficient now which is less because of the Fourier expansion term, and so you have a drop in efficiency. So, if you take a 50% duty cycle, I showed you that the drop in efficiency is about 40%. And so, but you can still have phase matching, and maybe you can use actually you can use higher nonlinear coefficient of the D tensor to achieve increased efficiencies, and this is now the standard technique which is conventionally used for most of the Chi2 processes. Okay, now if there are no questions, what we would like to next do is to look at exact solutions to the problem. Remember, we have solved the equation for E2 by assuming that the conversion from omega to 2 omega is of low efficiency, which means that I've assumed that E1 is a constant when I integrated this equation, either in perfect phase matching, either with no quasi phase matching or with quasi phase matching. And so that expression which I get can be used only for low efficiencies, maybe 5%, maybe 8%. But what will happen if my efficiency becomes larger? I can't use those solutions. So we need to look for solutions, and what I would like to do is to look at the solutions for a perfect phase match situation and get exact solutions to the coupled equations problem. So let me recall the two equations. So dE1 by dz is equal to I omega d by C n1 E2 E1 star, and dE2 by dz is equal to I omega d by C n2 E1 square. I am assuming delta k is equal to 0. Okay. What we did was we solved only this equation, assuming E1 is a constant, actually including the phase mismatch term, and we got a solution. Now I want to solve these two coupled equations and not to make this approximation of neglecting variation in E1. So let me give you a few steps here, and we will go to the complete solution in the next class. So what I do is, please note that E1 and E2 are the complex electric fields. So let me write E1 of z is equal to U1 of z exponential I phi 1 of z, E2 of z is equal to U2 of z exponential I phi 2 of z. U1, U2, phi 1, phi 2 are all real terms. So that's the amplitude of the electric field, that's the phase of the electric field, the amplitude of the second harmonic, the phase of the second harmonic. So I want to substitute this into this equation. So for example, let me calculate dE1 by dz is equal to dU1 by dz e to the power I phi 1 plus I d phi 1 by dz U1 e to the power I phi 1, which is equal to I omega d by C n 1 E2 E1 star. So U2 e to the power I phi 2 into E1 star, which is U1 e to the power minus I phi 1. Okay, I am substituting this into this equation. So E1 dE1 by dz is equal to I omega d by C n 1 E2 into E1 star. So if I take exponential I phi 1 on the other side, what I will get is dU1 by dz plus I d phi 1 by dz into U1 is equal to I omega d by C n 1 U1 U2 exponential I theta of z, let me call this, but theta of z is phi 2 minus 2 phi 1. Okay. Now I can equate the real and imaginary parts on both sides, and I can get two equations. So dU1 by dz is the real part. So I will have minus omega d by C n 1 U1 U2 sine theta of z, and d phi 1 by dz is equal to into U1 omega d by C n 1 U1 U2 cos theta of z. Okay. So what I have done is I have written the electric field as a product of the amplitude term and a phase term here, substituted into this equation, and this one equation here gets replaced by two equations here. Similarly, I can substitute for E2 and E1 in the second equation, and I get two more equations. So, let me write those two equations. Please check it yourself. du2 by dz is equal to minus omega d by Cn2 u1 square sin theta of z, and u2 d phi 2 by dz is equal to omega d by Cn2 u1 square cos theta of z. Four equations. Instead of two complex coupled equations, I have four coupled equations now, all real equations here in terms of u1, u2, phi 1 and phi 2, and how they vary with z. So, what we will do in the next class is to solve these four equations and get the solution, and I will show you that I can get the exact solution to these equations. These are under phase matching conditions only. So, effectively what we will analyze is, here is my crystal, delta k is equal to 0, and I have a frequency omega incident here with amplitude u1 and with a phase phi 1. What is it that is what is the u2 here that is getting generated? So, and this is the frequency 2 omega that comes out. So, we will be able to obtain solutions to the second harmonic, exact solutions under phase matching conditions, and later on I am going to use the same set of equations for the reverse problem of generating omega from 2 omega. Actually, this problem where instead of going from omega to 2 omega, I go from 2 omega to omega. This is called the parametric amplification, and I will use the same set of equations, and these equations are very interesting because they give me a complete analytical solution to the problem of second harmonic generation under phase matched operation condition. Okay, do you have any questions? Okay, so what we will do next class is to solve these equations and get complete solutions. Okay, thank you very much.